So in this video, I'll be talking about how air pressure, temperature, and altitude vary in an isotropic atmosphere. So first we'll start out with the equation of statics, the basic one. So dP. So here we got change in pressure over change in height is equal to negative rho times gravity. This is just explaining why it's negative. We could have chosen it to be positive, but I'm choosing it to be negative here at a certain atmosphere pressure at a certain point of 0 and a certain point of z. So now that we have that, let's write that again. Just do some algebra here. And then let's integrate. And for integrating, rho is constant in this situation. So and gravity is always constant. And so we're going from, let's just say, pressure 1 to pressure 2. This one we're going from some point 2 to some point 1. That is a 2, not a z. Now let's integrate. And so you'll get P2 minus P1 is equal to rho G Z2 minus Z1, or the change in Z. And this change in Z can also be written as, let's actually get P2 by itself. So we get P1 minus this Z2 minus Z1 can now be written as H. Since we are dealing with altitudes, it is actually height itself at this situation. For altitude, and I'm gonna have to start a new page here. So where we left off is P2 equals P1 minus rho GH. So rho is equal to pressure times the mass over RT. So now that we have that, and we know how to do those steps before, so I won't change the H this time. I'll restart at dP. See, instead of rho now, we'll use P and RT, let's say times negative G. And then we gotta get each one to each side. Integrate dP over P is equal to negative, so G RT over PM DZ Z2 Z1 P2 P1. We'll go up here, so then you'll get natural log P2 by P1 is equal to, let's see, it's the same thing as last time, so we're going to get negative G M P. Oh, yeah, there should not be a P here. That is my bad. So Z2 minus Z1 over RT. We can exponentiate this and move the P1 to the other side. And using natural log rule, I'm pretty sure it'll be P2 minus P1. So we'll get P2 equals P1 minus. And then now we have the pressure. So relating this to pressure, we have P2 is equal to P1 minus exponentiate this data. So now we're going to have to find the temperature. And so we're going to have to relate temperature to pressure using a different equation. So get a new page. And first we got to say this is an adiabatic process. I'm going to say work is positive. And also the system isn't ideal. If it was an ideal gas, then it would be nearly impossible to do for what I know of right now. So the system is an ideal gas. So here we'll use entropy. So du equals Q minus PdV. And here, well, since we're assuming it's adiabatic, Q is 0. Heat won't change. And since this dV here is specific volume, so in du here, you could change or substitute in. So once you substitute this in, you should get CVET is equal to, that's a 0, PdV, or this dV, is a specific volume. And then we can substitute the P for R T over V is equal to. And now we can just set each of both sides. So it should get rho CV dt T equal to rho R V dV. And then this needs a negative in the front. Negative, I forgot that. So this will be from some temperature. So T2, T1. This will be some volume. V2, V1. We integrate it, and we'll get CV log V2 equals negative R natural log 2 over V1. Right there. And then we can transform it. So that's still being equal to CV natural log of T2 over T1 negative R natural log T2 P2 T2 times P1 over T1. Using the ideal gas law, just manipulating it, this is what you would get. And that's still equal to that. Then we want to exponentiate both sides. So when you exponentially, you don't exponentiate both sides yet. It'll be actually easier if I write this out again. So it's CV log 2 T1 equal to natural log T2 P2 times P1 over T1. What we want to do, we want to get this R to the other side. That is what we need to do. So you divide it by negative R. And then by natural log, we can move that to the top before we exponentiate the equation. So natural log so it's raised to the negative CV over R power. And the rest of this is the same. You can raise them up to both powers. You'll get T2 over T1, since both these will go away. And then we can change what that is on that side. You can make it T2 over T1 times P1 over P2, which is what we're going to want to do. When you do that, you can do T2 times T1. So let's do 2 T1. We're moving it to this side. So you'll get 1 plus CV over R is equal to P1 over P2. And 1 plus CV over R. CV plus R is equal to CP. CV, actually CP by CV is equal to K, which is the ratio of air, ratio of specific heat of air to the specific heat capacity. So after that, we'll need this later. But we have isolated temperature and pressure on each side, so we have them related. So now we're trying to find temperature as it changes due to pressure. So we'll remember this equation here as I make a new sheet. So you get, actually, let me see more top. I believe it was a T2 by T1. 1 plus CV over R, it's raised to that power, is equal to the natural log plus T2 over, no, I already got that on the other side. This natural, well, it's no more natural logs either. This is P2 over P1 at this point. And I'll explain the rest of this in part 2 of my video, since I'm running out of time to screen record.